Hi, Mr. Richards here. Today's lesson is on solve systems of equations by graphing. Well, the first question we need to ask is, what is a systems of equations? Well, systems of equations is a collection of two or more equations with the same set of variables. And one way to solve a systems of equations is by graphing. So solve the systems of equations by graphing y equals negative x plus 5 and y equals 2x plus 2. Well, let's graph each of these using the slope-intercept form. Well, our slope in our first one is negative 1. Our y-intercept is 5. So we have a y-intercept of 5, and then a slope of negative 1 means negative 1 over 1. So we'll go down 1 every time we run 1. So we'll go down 1, run 1, down 1, run 1, down 1, run 1. There, 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 and there. And we can now connect these dots. Got a little off there, but if we label this then, this is the graph of y equals negative x plus 5. What about our second equation? We have y equals 2x plus 2, where we have a slope of 2 and a y-intercept also of 2. So we can start by graphing our y-intercept at 2, and a slope of 2 means 2 over 1, so we will rise 2 every time we run 1. So we will rise 2 and run 1. Rise 2 and run 1. So we go here and there. And so now we have our graph that we can draw in right about there. And that is the graph y equals 2x plus 2. Now what does that actually mean? What are we looking for? We're looking for an intersection point here. And you can see that we have an intersection point right there. And that is at 1, 4. And so as I solve the systems of equations by graphing, our answer is 1, 4. Now it is possible to check these as well. What I can do is go, all right, my first equation was y equals negative x plus 5. Well, if my answer is 1, 4, then what I can do is put in 4 for the y and 1 for the x and solve. What do we end up with? 4 equals negative 1 plus 5 is 4. So it works for that equation. What about my other equation? We have y equals 2x plus 2. Well, if we put in 4 for the y equals 2 times 1 for the x, four then equals 2 times 1 is 2 plus 2, and sure enough 4 equals 4, so this also checks out. So my solution is 1, 4 for this systems of equations. Katori and Mark each downloaded songs. Mark downloaded 4 times as many songs as Katori. Mark also downloaded 6 more songs than Katori. Write a systems of equations to represent this situation. Well, let's set our variables first. Let's let y equal Mark, and let's let x equal Katori. Well, in this example, then, Mark downloaded 4 times as many songs as Katori. So we could say Mark y equals 4 times the number of songs Katori had. Y equals 4x. And then the other equation we have is Mark, which is represented by y, equals 6 more songs than Katori. So Katori's was x. 6 more than that is plus 6. And so that's our system of equations to represent this situation. Now, part B. Solve the system of equations by graphing. Explain what the solution means. Well, when we look at our y equals 4x, we have a slope of 4 and a y-intercept, well, that's 0. So we have a y-intercept of 0, and a slope of 4 means rise 4, run 1. So we will rise 1, 2, 3, 4 every time we run 1. And again, rise 1, 2, 3, 4, run 1. And we can draw this in. And this was our y equals 4x. As for Katori's, or the next equation that is, our slope is 1, and our y-intercept here is 6. So a y-intercept is 6, and a slope of 1, which is the same thing as rise 1, run 1. So we will rise 1, run 1, rise 1, run 1, rise 1, run 1, which puts us here, there, here, and now we can connect. And that again was the equation y equals x plus 6. And do we have an intersection point? Yes, we do. That intersection point is right here, which if we look down at our x-axis is 2, and here is 8, so that is at the point 2, 8. So what does the point 2, 8 mean? Well, x equals 2 and y equals 8, which means our x was Katori and our y was Mark. So we could say Katori downloaded 2 songs and Mark downloaded 8 songs. And even if we were just do a quick check, Mark downloaded 4 times as many songs as Katori. Well, Katori was 2 times 4 is Mark's 8. And also 6 more songs. Well, Katori was 6, or 2 plus 6 is that 8. So we can write systems of equations for real-world situations and solve them by graphing. And in our third example of solve system of equations by graphing, our first equation, y equals x plus 2, is already in slope-intercept form. However, x plus y equals 2 is not. So we can start off with just the first one, y equals x plus 2, where we have a slope of 1, which is the same thing as 1 over 1, and a y-intercept of So we can graph the y-intercept at 2 and a slope of 1, up 1, over 1, up 1, over 1, up 1, over 1. Now we can do something kind of unique here too. Is 1 over 1 the same thing as negative 1 over negative 1? Meaning, can I go down 1, back 1? Down 1, back 1? Sure, it is the same. So I could go down 1, back 1, down 1, back 1, down 1, back 1, down 1, back 1, and really draw out my line. And as I connect our points on the graph here and label, we have y equals x plus 2. Now the challenge in this question comes in our x plus y equals 2. We want to write this in slope-intercept form. We want to write this so our y is alone. So in a way, we're solving for y. How do we get the y alone? We need to move this x. And if we subtract this x on both sides, what we're left with is y equals negative x plus 2. So we have a slope that is negative 1, which is the same thing as negative 1 over 1, and a y-intercept now of 2. If we're going to be graphing using slope-intercept form, we need to make sure we're in slope-intercept form. Well, our y-intercept of 2 makes this kind of non-suspenseful. A slope of negative 1 means we're going to go down 1, right 1, down 1, right 1, down 1, run 1. So down 1, run 1, down 1, run 1. But is this the same thing as 1 over negative 1? Meaning we can go up 1, back 1, up 1, back 1? Sure, up 1, back 1, up 1, back 1. Can help us to complete this graph. And so as we connect our points here, again, almost non-eventful because our intersection point happens to be on the y-intercept. We'll make sure we finish this one the right way. This is the point 0, 2, and of course not 2, 0. So 0, 2 is our answer, and we are able to check this. And the way we can check this is to say, well, my first equation, y equals x plus 2. If I'm saying that 0, 2 is my answer, if I put in a 2 for y and a 0 for x, does this work? Yes. 2 equals 2. What about my other one? X plus y equals 2. Well, if I put in a 0 for x and a 2 for y, does this equation work? Sure. 2 equals 2. So my answer here is 0, 2. In my fourth example, solve the systems of equations by graphing. We have y equals negative x minus 3, and we have 2x plus 2y equals negative 6. Well, I can graph this first one without too much of a problem. Y equals negative x minus 3. We have a slope that is negative 1, which is the same thing as both negative 1 over 1 and 1 over negative 1. And a y-intercept that is, now careful here, it's not a positive 3, it's minus 3, a negative 3. So our y-intercept here is down here at negative 3. And a slope of negative 1 over 1 means down 1, right 1. Down 1, right 1, or up 1, back 1, up, back, up, back. And so I can draw this line in here. And I can label this y equals negative x minus 3. Now my next equation is not in slope-intercept form yet. We have 2x plus 2y equals negative 6. Well, I need to solve for the y. So if I subtract 2x from both sides, I have 2y equals negative 2x minus 6. And then I need to divide everything by 2. This cancels, and I'm left with y equals negative x minus 3. Wait a minute. We just graphed that. Our red line was y equals negative x minus 3. So I have the same line here. These are essentially the same equation. And so what does that really mean? Well, both equations have the same graph. Any ordered pair you put in here will work for both equations. Therefore, there's infinitely many solutions for the systems of equations, and in fact, that is our answer. We can write infinitely many solutions. Now we have solved this system of equations by graphing y equals 2x and y equals 2x minus 4. Well, both are in slope-intercept form, so if we go ahead and take our y equals 2x, we have a slope of 2, which is the same as 2 over 1, or as we discussed earlier in this lesson, negative 2 over negative 1. And our y-intercept here, well, we have nothing in the place of b here, so we're just going to call it 0. So a y-intercept of 0, a slope of up 2 over 1, up 2 over 1. Or, once again, down 2, back 1, down 2, back 1, down 2, back 1. And we can connect these and label this graph y equals 2x. Now what about our next graph? Y equals 2x minus 4. Well, here we have a slope, once again, of 2. And we have a y-intercept. It's a minus 4, so negative 4. So our slope is 2 over 1, and we have a y-intercept of negative 4. So we'll go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I haven't found an intersection point yet. Well, if we go ahead and draw in this line, you should notice something here. What is the relationship between these lines? Well, in fact, these are parallel. We have the same slopes. You can see how it's the same slopes even on the graph, but different y-intercepts. And when that happens, we actually have no solution. And that, in fact, is the answer. There is nothing I can put in for x and y to make these two equations equal each other. Which takes us to our key concept box. There are 3 answers that we can get right now for systems of equations. We could get one solution where we have the one intersection point. We could have no solutions when we have the parallel lines, like we just had, where we had same slopes but different y-intercepts. Or we could have infinitely many solutions when it looks like it's the same line. And that's exactly what this note summarizes. Different slopes will have one solution exactly somewhere on the graph. And if we have the same slope but different y-intercepts like we do right here, there's no solution. But when we have the same slope and same y-intercept, we'll have infinitely many solutions because it'll just be the same line. And that is it for this lesson on solve systems of equations by graphing. Good luck.